All right, so we're going to talk about functions today. And in order to kind of motivate the discussion, let's start with what is a function and think here based on what you remember from math classes. So what's a function in math class? Bueller.
It's like a process. So you put like a number in and then you can add it, multiply it.
Right, okay. So you guys kind of think about this. Right, number comes in, number comes out, and there's some sort of formula that describes what exactly happens. So, something like this, right? Just a simple function. Um, and, maybe you could also consider, for example, what the set of numbers that this thing is allowed to work between. So, like you worry about the domain and the range and all of those sorts of things. Okay, so here I've got a function that takes in some sort of real number and spits out some other real number. Essentially, all the functions that you guys deal with in math, or at least have up until this point, have been something like this, right? Now, maybe the formula is a bit more complicated, or maybe it's a bit more exotic, like, for example, it has multiple variables in it. Is that okay? Right? And okay, maybe you haven't had to deal with a lot of multivariable functions, but they certainly do exist. And you know what's really fun, by the way, is calculus when you're dealing with multivariable functions. That is rad. Yeah. You guys like calculus? No, you don't like calculus. Okay, so right, so functions in math class are essentially everything that you've encountered is something of this form. But I'd like for us to kind of slightly expand our definition to something more like this. Meaning that our function can sort of accept as input any kind of object, any sort of mathematical or quasi-mathematical object, and it can output any other kind of mathematical object. These things don't have to work just on numbers, okay? They could work on other things. So maybe a good example would be something like, let's say that I specified something like this, where I have some function and I stick in a bit of text and it outputs a number. Well, that's more general than the functions that you've dealt with, at least in the math classes y'all have been in. Um, and in this case, 6 didn't come out of thin air. What is 6 in this case for that particular input? Yeah, it's the number of characters, okay, excluding the quotation marks, right? So I could have something that works on text, and I don't have to return numbers. I could also return text or any other kind of object. Now, in some sense, this is maybe an artificial distinction because, well, how really is hello encoded on a computer? Hmm? Yeah, how is each letter encoded? In binary, but specifically in ASCII, right? Or maybe in Unicode for like emojis and stuff. But point being, it's all ultimately in binary, so ultimately everything is just numbers anyway. In which case we're kind of back to math class kind of stuff. It's just we think of specific numbers as being interpretable as representing letters or numbers or something of that sort. Okay, so um, right, so we can think a little bit more generally about what we mean when we say function compared to what we do in math class. And in particular, what we can do is um, a function actually doesn't have to take in anything, and it doesn't have to spit out anything either. Okay, we can have a function as is something that takes in nothing, spits out nothing, but does stuff. Okay, so um, what that looks like will maybe become a bit more clear on the computer, but it doesn't have to actually take anything in or return anything. Okay. Now, in math, those types of functions, they certainly exist, but you probably have never actually used one because you wouldn't probably run into them until one of two things. Either you're in a computer science class, well, here you are, or you're a math major and you're taking a bunch of courses in mathematical logic and stuff like that, which I don't know, maybe it will come for some of you, but yeah, okay. So that's sort of the idea, right? We can certainly do number comes in, number goes out, but we can also do more general things. Okay, so any question, preguntas, and or fragens at this stage? Oui? Okay, so let's go over to the computer and let's start making some functions. All right, so let me start a new file. Oh, geez. Oops. Okay. I need that for reasons that'll become clear later. So let's just define some sort of simple function that can square a number. So in math notation, we would write something like that or x squared or x times x, right? Just a perfectly good function. And here's how I would write something that does that. I'm going to define a function and I'm going to call this the square function. And it's going to take in some number x. And then the answer is the product of x times x, and I'm going to return x. Okay, so I have defined that function. It took 3 lines of code. I could have actually just done, this is maybe a little easier to just say that, that's valid. For reasons that'll become clear later, I'm going to go ahead and just write x times x here and then return the answer. So I'm thinking of, okay, a number comes in, its value is x, I multiply it by itself, I call that value, the product of the two, the answer, and I'm going to return the answer. Okay, so does that make sense? All right, now if I want to actually use this, then what I have to do is actually call the function with some sort of actual input. So me defining this thing is kind of like writing down the formula f of x equals x squared. It defines it, but I haven't actually used it for anything until I plug in a specific number. Okay, is that all right? All right, now, not shockingly, what should happen if I run this? Well, what happens? Looks like absolutely nothing because how about I need to print it? And sure enough, what do we get? 25. Okay, that's good. Our function works. Okay, so the parts of this, because I'm writing this in Python, uh, the the pieces that I need here, I need to say def, short for define. So I'm defining a function. And what am I going to call my function? Square. I mean, I could call it whatever I want, basically, but I'll call this one square. And then what kind of input does this depend on? Well, it depends on something called x, and what kind of object is x here? Yeah, it's some sort of, well, but what type of variable? Object variable, those kind of mean the same thing to me. But what kind of thing is it? I mean, how am I using it in the function? Right. It represents some sort of number. Okay. And maybe what I should say there is, well, would it make sense to plug in a letter for x here? Why not? Well, what does it mean to multiply a letter by I don't know what that means, right? But it does make sense to multiply a number by a number, right? Okay, so um, did I ever say, though, when I was defining this, what kind of object x was? No, I just said x. And from context, was it clear that x is? Like from the context of what I've defined or what we're kind of talking about. Do I need to walk around with a stick and start beating you guys until you wake up? This can be arranged. No? All right, I'm walking over and getting a stick. So what is x? What kind of thing is it?
A number.
A number. Thank you. Okay. I think I've cracked how to keep you guys moving. Yeah. So it's some sort of number, but I never said what kind of number it was in the parentheses thing there. Okay. Now, the reason I want to kind of say that is because this is one thing about Python that I dislike. Did I ever have to even specify what kind of number x was? No, it's just a number, okay? But as we've seen in terms of encoding, what different kinds of numbers have we dealt with in terms of encoding them? Whole numbers are integers, okay? And those could be signed or unsigned. And also things with decimals, which is to say floating point numbers. Okay, so we never specified here whether or not the x was even a whole number versus a floating point number. Python lets you get away with not caring about that. Other languages like C are much more picky, and you can't. Okay, so in this case, I had a function that only took in a single value, x. And I called that thing x. And it just multiplied x by itself. It returned an answer, and great, everything's cool. So what other things could we change here? Just for sake of example, or other functions we could write. And feel free to be inspired by math classes. No? Yeah. Okay, so I could do like f of x equals 6x, or I could even do something like this. Now, I would never actually do this in practice, but I could, right? So how about I take in two values, I multiply them, and I spit out the product of the two. Okay. Now, the reason I say I would never actually do this in practice is because I would just write x times y and be done with it. But for sake of demonstration, this is certainly fine. But what would I call here? Multiply, and then I need to specify how many numbers? Two. All right, so pick two numbers. 3 and 4. Okay, and so what should we get out of this? I would hope that we get 12, and sure enough, we do. Okay, so this function accepted two objects and returned a single object. Two numbers went in, one number came out. It's a kind of contrived and stupid function, but I could do it, right? Okay, were there any numbers that we weren't allowed to plug in for either of these functions? Can I plug negatives into either of these? Sure. Is there any problem with multiplying two negative numbers? Huh? Asking the wrong guy? Okay, but what is sort of a problem? So where are negatives potentially an issue? What kind of function might have issues with that? Yeah, a square root function, for example. Okay, so let's actually write such a thing. Okay, so Python does have a square root function built in. It's called sqrt. And so I'm building my function out of its function. So what would happen, oops, what would happen if I called this function square root of 5? Okay, let's call the square root of 5. And what do I get? Yeah, 2 point whatever. Okay, 5, it's saying, oh, well, that's a number, and I can take the square root of it. And here it's computing it as a 64-bit float, just sort of natively. Okay, we get 2 point whatever. Great. Not all that interesting. But what happens if I try something stupid like this? Okay, should we expect to see some sort of error? Yeah, I would hope so. Okay, and what's the error that it's given us? Math domain error. So what's the problem with taking the square root of -5? Yeah, you get imaginary numbers or something. Okay, so let's actually change up our function to maybe do something slightly different. Okay, and in particular, can I mix conditionals? I could do something like this. Okay, so I can put conditional expressions inside of a function. Now, that's not something that we often do in math class. There is actually one good example of it. Can anybody think of an example where you have an if kind of statement in a math function definition? No? No? Where a function is defined in two different ways depending on the input value? Here's a good example. How's the absolute value defined? Okay, that's sort of a geometric definition. Algebraically, how would you define it? Okay, so let's continue on that line, right? If negative, flip it to positive. If it's already positive, just leave it alone. Okay, so you would write something like this: if x is bigger than or equal to 0, return x. Otherwise, what do I do? Well, if I have a negative number and I stick another negative sign in front of it, what happens? The negatives cancel and I get a positive. Okay, so that right there is the way of defining absolute value. Now let me write this in math notation up on the board. How many of you guys have seen it written like this? Yeah? How many of you guys are in calculus this semester? And surely you've written that out at least once this semester, right? No? Yeah? Okay. Um, yeah, okay. So great, right? We can do that kind of conditional thing. And if we return to our example with the square root, right, what's the idea here is that the value that this function is going to return, it can't do it for certain inputs. You can't take the square root of a negative. Or let me rephrase, can you take the square root of a negative? Okay, if you do, what kind of mathematical object do we get? Something I, right, an imaginary number, right? So if I ask, like, can we take the square root of a negative and get a real number answer, then no, we do not, right? An imaginary number is not a real number. Um, If we are perfectly cool with working with imaginary numbers, then, well, just do it, right? What's wrong with an imaginary number? Okay. All right, so let's test both of these functions and make sure that they work right. Okay, so now what should happen if I do the square root of -5? It should say you're a moron, or you moron, okay? But also, what else did it print here? None, okay? Because in the case, what did I return in the else case? I printed something, but is that the same as returning? No, I never actually returned anything. So it has returned this object called none, okay? And that's just because I'm an idiot, okay? Now, what about the absolute value? Could we do the same thing for it? So let's do print abs val of 5, and let's also do print abs val of -5. Good. So what should we get printed this time? 2 copies of 5, right? What's the absolute value of 5? 5, it's already positive. And what's the absolute value of -5? -5. Or I mean 5, sorry. Yeah. You can tell the rocket fuel hasn't quite kicked in yet. So, okay. So does that kind of make sense? Yeah? Okay. All right, so let me define another function, and this will kind of give us a preview of coming attractions. Okay, so I'm going to write a function that takes a number and raises it to a power. Okay, seem like a perfectly good, oh, and I need a colon, perfectly good mathematical idea, right? So how could I define this function? Well, what happens if the power is 0? Okay, yeah, what's anything to the 0? 1. So if we could say if pow equals 0, return 1. What about if the if the power equals 1? Yeah, so what's anything to the 1? Itself. Okay, so those are kind of the two silly cases. But what would I do if, let's say that I had a number to the second? How do I want to think of that? So like, or let's take a larger number for sake of demonstration. What is 2 to the 4th? 2 times 2 times 2 times 2, right? Which happens to be 16. Okay. How could I think of multiplying 2 times itself? How many times did I multiply it by itself? The number of the power, it's actually that -1 because 2 to the 4th, how many actual multiplications do you do? 3, not 4, but okay, whatever. Well, what's the code, or when I say code, I mean this in a non-technical sense. Repeated multiplication, right? That's a repeated process. What kind of programming construction do I want to use for that? Huh? A loop, okay? And so how about this? Okay, let me define the answer equals 1. That'll become clear in a moment. Could I do something like this? Oh, it's not n, it's number. Okay, so what is this going to do? Well, let's say that we're doing 2 to the 4th. Okay. So for I in range 0 to pow, what's pow in this case? 4. Okay. So for I in range 0 to 4, what values does I take on? 0, 1, 2, and 3. Okay. And what's going to happen if I is 0? Well, what's answers start at? 1. Okay. What's 1 times 2? 2. Okay. Answer is now 2. Now I is 1. What's 2 times 2? 4. Now I is 2. What's 4 times 2? 8. And then finally, what's 8 times 2? 16, right? So just multiplying, kind of cascading up. Now let's make sure that the function actually works. So what, okay, so I need to do, let's print, what did I call this thing? Power of, let's do 2 and 4. So 2 to the 4th is what this thing is computing. And, oops, does it work? Yes, we got 16. Okay, so does that kind of make sense? Yeah. So what I've done though is, so think of it this way, right? What did we talk about last time? We talked about conditional expressions and we talked about looping expressions, okay, or iterative expressions. What did I just do here? I've mixed them, right? Well, pretty much every computer program under the sun is some mix of all of those, right? It just may be really, really big and complicated. Well, there we go, okay? And these things can be on the insides of functions. Now, can anybody tell me an example where you might have something that looks kind of like this in math class, where you might have a function that actually has sort of a complicated definition that looks sort of like this? And this one was kind of contrived, but there's other better examples. Any guesses? All right, let me write one, see if you guys agree. All right, so what have we done? We've taken a number here. We just take the number 5. What does this mean? It doesn't mean to like shout 5 really loudly, does it? It's the factorial function, okay? What is 5 factorial? Well, gee, that seems like code for doing some sort of function with a loop. Huh, right? Okay, so what is 5 factorial? How many of you guys have seen the factorial before? Who's never seen the factorial function before? Okay, here's where you would see it or where you would use it. Okay, let's suppose that you are going to go away for 5 days of vacation and you wish to pack a suitcase with exactly 5 t-shirts in it. And then you get to your vacation and let's say, okay, you've got a Metallica t-shirt, a Megadeth t-shirt, a Beavis and Butthead t-shirt, a Wabash t-shirt, and I don't know what would be another good t-shirt. A plain t-shirt that has nothing on it. Okay. How many different orderings are there for you to wear those t-shirts? Huh? It's way more than 25. It's 120, which is 5 factorial. Okay. Well, let's think about why that's the case. How many t-shirt options do you have on Monday? 5. How many t-shirt options do you have on Tuesday, assuming that you don't rewear a dirty t-shirt? 4, then 3, then 2, then 1. Okay. Let's say you wear the Metallica t-shirt on Monday. Does that influence which of the other 4 t-shirts you wear on Tuesday? No. So that decision is independent once you've got those 4 t-shirts as your option. So the number of ways multiplies. So you have 5 choices on Monday, 4 on Tuesday, 3 on Wednesday, 2 on Thursday, and there's only one clean t-shirt left on Friday. And all of those decisions were independent, right? So it'd be 5 times 4 times 3 times 2 times 1, which happens to be 120. Okay, so that function, or this idea of multiplying 5 times 4 or whatever down to 1, comes up often enough in mathematics, specifically in like probability and things like that. It's not the only place it comes up, but that's sort of where it's sort of you're maybe most likely to first encounter it. That we have a name for this thing, and we call it the factorial function, denoted with the exclamation mark. Okay, so let's program this thing. Okay, so there's a couple of conventions here. What is 1 factorial? Well, what do you think it is? 1, okay? Because you're taking all the numbers from 1 down to 1 and multiplying them in sort of descending order, but you're already there at 1. Okay, here's maybe an easier way to think about that. You have precisely 1 t-shirt. How many arrangements are there for you to wear that 1 t-shirt? Well, 1, you only have 1 freaking t-shirt. Okay, so the base case here would be if the number is 1, the answer is 1. Okay, now this one's going to drive you guys crazy. What about if the number is 0? What's 0 factorial? It's kind of a silly, nonsensical question when you think about it, right? But it actually does have a good answer. And that answer is 1. Here's how I like to think about it. How many different arrangements are there for you to order 0 t-shirts? Well, there's 1 way to do it. You have no t-shirts, right? There's definitely not more than 1 way to do it. And there's definitely not 0 ways to do it because, well, you've done something, right? So 1 kind of makes sense. That's maybe not the best explanation. You could also just sort of take it on faith that we just defined it to be 1 and shut up and don't argue. Okay, but that's how I kind of like to think of it, as making sense to choose 1. Okay, good. All right, if the number is bigger than 1, what do I do? So like 5 factorial, how did I compute that? Multiply everything from 5 to 1, okay? And if I'm going to do that, let me define here, actually, let me define answer to be 1, and then in this place I can just return answer instead. Okay, but my else case is going to be, for I in range 1 to num plus 1, ants equals, well, actually here, I'll just do it this way. No, I want to do this. Ants equal ants times I. Okay, so what does I start out as in this loop? 1. Okay, what is the final value of I in this loop? Okay, it's just number. Okay, so remember in Python, how would I write this in math? I'd write it something like that, right? So This is the annoying thing about the loops in Python. 1 is included, but num plus 1 is excluded. So that's why I added 1 to the number, because how many times do I need to do this? I need to go from 1 all the way up to n. And to go up to n, I need to say, well, go up to n plus 1, but exclude that one. Okay, I know that's annoying, and I'm sorry that that's the way Python does it, but say la vie. Okay, and then I'll just multiply everything. So I'll do 1 times 1 times 2 times 3 times 4 and so on. So in this case, which direction am I counting? I'm counting upwards, but how did I define the factorial function? Counting down? Could I reverse this to count down? Sure. I can go num plus 1 to 0, counting by negative ones. Okay, so that would work. All right, let's test it and make sure it works. Oh, and then I need to return ands there. And then let's print factorial of 5. And so what should we get? Oops, I've made an off by 1 error. No, damn it. Did I save it? And oh, sorry. In this case, it is num. There we go, 120. Okay. Right, so there we go. So what did this loop do? It did 5 times 4 times 3 times 2 times 1, and then that was it. And we got 120, which, great. Okay, so questions about that. I'm going to switch this function around and make your heads explode. No? All right. So let's think about this factorial in a different way. To motivate this question, let's consider an onion. Okay, and in particular, what's the most delicious thing you could possibly do with an onion? Eat it raw? You people are monsters. Yeah, wow. I don't know about you guys, but I really like what Outback Steakhouse does with them. Right? The bloomin' onion where it's like split open and battered and deep fried, and then with that delicious, super bad for you ranch sauce or whatever it is. Yeah? No, you don't like them? You have any idea how many calories are in that thing? Like per person, right? You know, the whole bloomin' onion's probably like 10,000 calories or something. Okay, so if you were to eat the outermost ring of bloomin' onion petals, what are you left with? A slightly smaller blooming onion, right? It's kind of like if you peel an onion, right? So an onion has got a bunch of spherical shells around it. If you remove the outermost spherical shell, what are you left with? A slightly smaller onion. Yes, and if you remove that outer layer, then you are left with a even slightly smaller onion, and eventually you get down to that little core bit, which unless you're dicing your onions, you throw away, right? If you want to make onion rings, you don't use that little core bit in the middle. No, none of you guys have. Who's never chopped onions in your life? There's a fine art to doing it, but yeah. Well, yes, but once you've got the sharp knife, even the technique for how to chop it is there's good technique there. Okay, so point being, the onion, right, has layers, and you can think of what's inside as being a smaller onion, right? What's another way that I can, or so what is 5 factorial? Let me just write this out on the, well, actually, I'll type it. I'll type it as a comment. Okay, so how did we think of 5 factorial? We thought of this as what? 5 times, 4 times, 3 times 2 times 1. All right, here's how I think about 5 factorial. Well, I look at the 4 times 3 times 2 times 1 and I say, that's a factorial. So let me write it that way.
Then we'd have to define each factorial.
I would, but I wouldn't. Okay, because here's how I really like to think about it. Well, let me think of it this way. Okay, I'm going to think of this like an onion. I can peel off the outer layer of the onion, and what's left inside is just a slightly smaller onion. Okay, but there's one key to this, which is I have to know what to do with that innermost layer of onion, right? The onion isn't infinite. There's some stopping point, the little core at the center of it, right? Well, that's like me specifying that 0 factorial is 1. Okay, so let me redefine this function. I'm going to make a new version of it. Okay, and I'm going to call this rec factorial. What the rec means, well, it's because I'm about to wreck you guys. Now, all right, so if num is 0, what should I return? 1. Else, you guys are going to hate me. I'm going to return that product. Okay, now how many of you guys think what I just typed is exceedingly slimy, dirty, miserable? I'm a horrible person for even thinking of doing this. Why, Liam, do you think I'm a terrible person? Well, okay, you might have many reasons to think I'm a terrible person, okay? But specifically with this function that I've just written, why am I a terrible person? What bothers you guys about that function? Oh, other than the fact that I forgot a colon.
It's one of many.
One of many things that makes me a terrible person. Okay. So look at it. Yeah, Xander? Exactly. I have a self-referential function. So the function is defined in terms of itself. Do you have a problem with that? Or does it feel slimy? Yes, but it is perfectly mathematically valid to do so. And the reason is, each time I call the function, I'm calling it with one smaller input. This would be a problem mathematically if that process never stopped. But does it ever not stop? No, because what do I have here to catch myself? I've got a base case, right? I know that my onion could have a billion layers, but no matter how many layers it has, what's definitely at the center of it? That little core piece, okay? So no matter how many layers it has, I can always peel off one layer and consider the problem with the remaining slightly smaller onion until I get down to the core. But I know that I'm always going to get down to the core because I programmed it that way. And the factorial is defined that way. Okay, so does this feel dirty that I have a function that refers to itself? Yes, okay. But it is perfectly valid to do so as long as you have a base case to catch. Okay, when we do this, this is called recursion, when you have a self-referential function. Okay, and to understand recursion, you must first understand recursion. Yeah? Feel scummy? Well, get over it. Okay. All right. So, how many of you guys followed my instructions from last week and stocked up on your headache medicine over the weekend? No? You thought I was joking, weren't you? Okay, so this is an instance of what we'll call recursion, and that's what we're going to spend the rest of the week talking about. Okay, is how to think this way and why thinking this way can be advantageous. Okay, Liam, you don't seem enthused. Yes, exactly, right? As an English major, like if you saw this in a dictionary, you would be very, very displeased. Well, fortunately, this isn't English, right, or any other language. Okay. Yeah. Now, there are limits to recursion and how one uses it sort of responsibly, shall we say. Okay. But this is the idea, right? So let's think back to the factorial, a concrete example. What is 5 factorial? Well, it's 5 times whatever 4 factorial is. Well, what's 4 factorial? 4 times whatever 3 factorial is, and so on until I hit what's 0 factorial? 1. Okay. So if, for example, let's say that I had told you, well, let me think of it this way. What is 6 factorial? Whatever 5 factorial is times 6. But do we already know what 5 factorial is? What was it? 120, right? Because we already computed it a bunch of times. And so do I have to recompute the 5 times 4 times 3 times 2 times 1 part? No, because we already know it. All I have to do is take that thing and multiply by 6. Well, that's pretty convenient. Yeah. So we get 720 instead of 120, right? Without having to remultiply all that crap back out, right? But that's an example of recursive thinking. Okay. So other examples where you can kind of think of it this way. So the onion is a maybe cheesy one. How many of you guys have ever seen? They're called Matraiska dolls. This sort of Russian doll, right? So what do those look like? It's a big doll, and you open it up, and what's inside? A smaller version of the same doll, and then you open that one up, and inside is a small, and then eventually you get down to like this really, really teeny doll that looks just like the big ones, but it's really teeny, and that's where it sort of stops. Okay, so recursion is sort of the art of thinking of things as being nested in some sort of way, and the factorial function is that's a super common mathematical one that we use all the time. There are others, and we'll look at some of those others on Wednesday and Friday. Okay. So on Wednesday, prepare to come play with a toy. Okay? All right.